Hi, I'm Jared Pratt, and this is my senior design presentation on a development of a Terrier Motorsport aerodynamic package manufacturing strategy. I did this project with 3 others within the College of Engineering, Lionel De La Torre, Ian Connors, and Andrew Schmid, and our advisor was Anthony Lin. So first off, we're going to start with the problem that we're trying to solve. Terrier Motorsport is a club on campus making an electric formula vehicle for an FSAE hybrid competition. As such, their aerodynamic team needs to be able to manufacture their components in-house with a reliable and cost-effective method for current and future years. So before going into what my project actually was, I'm going to go into some of the general ideas of aerodynamic components. So if we look at the free body diagram on the far left, you can see some of the general forces acting within a car. 2 that we want to focus on for aerodynamic components are the downforce and the force of drag. The force of drag is a resistive force. It resists the car moving through the air, and as such, we want aerodynamic components seek to limit this force. And the downforce is a force generated by the aerodynamic components to increase wheel traction with the ground. These are the parts in the Terrier Motorsport aerodynamic kit that have been designed by the aerodynamic team or one of the other senior design teams working with us. We have a front wing, rear wing, and a nose cone. That rear wing is essentially a spoiler to give a better idea. And to better visualize, this is the Carnegie Mellon formula vehicle that they design, and you can also see the general locations of where those components will end up on the Terrier Motorsport car. So at the very beginning of our project, we met with our stakeholder to address some of the constraints that we are working under and what they want from us. This largely came down to budget and space. With the club being relatively new and having multiple teams, they need us to be able to advise a strategy that they don't need to buy excessive tooling or parts to be able to complete the manufacturing of their components. As such, that was one of our greatest limitations within the project because they need to be able to replicate it in future years. In addition, what we recommend needs to be safe. Previous manufacturing of these components has left behind hazardous dust, which is harmful to breathe in, so we're seeking to limit that as well. And finally, the parts that we recommend need to be able to withstand the forces that they need to be able to withstand the forces that will be acting on them as they're going. So as such, they need a strong enough compressive and tensile strength, a low surface roughness to reduce drag, and be lightweight, because if you're just adding a bunch of extra weight to the car, it's just going to serve to slow it down. So what is our project actually delivering? It essentially is a manufacturing strategy document or binder. This binder will be separated into 2 main ideas. First one being a how-to manual, and the second of which being some of our material recommendations. The how-to manual will go over how to create common geometries and assemble them. This includes airfoils, as shown here, and flat components to essentially walls for these components, and then how to assemble them together based on our testing that we do throughout our project. In addition to that, we are providing guidelines for post-processing these parts. Post-processing is just the removal of extra material or getting the desired surface roughness as well. And as I said, the material recommendations will be given through the testing we do in our project. So next we have the testing and what we chose to go with. We chose to create a composite manufacturing strategy. More specifically, a vacuum bagging composite manufacturing strategy. Composites are the merging of 2 materials to obtain a desired material property from the both of them. So an easy one to focus on would be fiberglass cloth and resin. Fiberglass cloth is strong in tension, however, it's a cloth and it just folds in compression. Meanwhile, resin is known to fracture in tension, but is very strong in compression. By combining fiberglass cloth and resin together, you get a part that is both strong in tension and compression. And we chose a vacuum bagging procedure largely because it allows for a greater penetration of that resin, which essentially just makes a stronger part. So as you can see on the far left, we did small batch testing. This was largely used for our flat and angled components, and it gave us a general idea on what we were recommending for our project later on. So as I said, how-to manual has multiple parts within it. You can see the vacuum-bagged flat component on the far left there. Most of our testing went over the main areas that we needed to focus on for this how-to area, so we were pretty well set there. Then we went on to creating foils. The nice part about composite manufacturing is that you can lay the composite cloth and resin over a bunch of different molds and geometries, and as such, because we are trying to make a lightweight component, we ended up going through and trying to iterate making the lightest 3D printable inner mold or core because that is an easy tool available to them through the College of Engineering, and as such, they wouldn't have to buy a new CNC foam cutter. And finally, we created, using the test components that we created, we would then assemble them for a general how-to. The final section of the how-to manual being the post-processing. Here is one of the parts that we did post-process. The main ways that we could post-process them was filing using a water jet cutter or a grinder cutoff wheel. The biggest issue with post-processing is it is the greatest safety risk area. It is very easy to breathe in these fiberglass fibers, which causes lung damage and other undesirable things. So our final recommendation was a angle grinder cutoff wheel in a well-ventilated area, seeing as it provides greatest amount of room that we could work with. The water jet cutter was too small, but the angle grinder is essentially done by hand. And finally, we have the deliverables of our project. It's a how-to manual. Right here on the left, you can see the general outline for our vacuum bagging instructions, but on top of that, we also created standard operating procedures, or SOPs, that are essentially a picture guide step-by-step, so it's easy to follow for the club once us as seniors are gone. And that is the end of my presentation. Thank you.
All right, we have a couple minutes for questions.
Can you address some of the issues you encountered with developing the 3D printed molds for the positive molded parts?
Yeah, so you can see the bottom image right there was actually our first 3D printed mold. When we designed it initially, we were trying to cut out as much support from the inside as possible. And when we did that and put it under the vacuum, it got crushed. It wasn't what you would want from a foil. The edges were caved inward. So we then went back to the drawing board and went to create a print that had no internal supports generated by the slicer. A slicer is essentially what takes your model and it'll convert it into a G-code file, which essentially just means that the 3D printer can read what that file is, and it's a set of instructions for the 3D printer to make it. So we went back to the drawing board multiple times to make a part that we could design specifically for the print and not have to rely on the slicer to create those internal supports, because those internal supports added a bunch of extra weight.
What was your experience like working with these different, you worked with 3 other people? 4
other people, yes.
What was your experience like working in that big of a group for
So
this?
it was nice because one of my group members, Andrew, actually did composite manufacturing for one of his internships in a previous summer. So that gave us a good starting ground. We weren't quite trying to grasp how to start here. So we essentially started by using his knowledge on creating those test coupons, and that served to actually teach us a lot of what we needed to do. And then from there, we each kind of took up a section to complete this project, one of us worked on a lot of documentation. I focused on that modeling and 3D printing area, and another one of us focused on the assembly side of things.
We still have some time for questions if there are any left. Okay, thank you, Jared.
Thank you.